We're going to go through 4 examples of solving radical equations, and we're going to talk about extraneous solutions. All but the first will have extraneous solutions. And let's talk about what that means for a second. As we get into the second, third, and fourth example, I want you to keep this in mind and see if you can connect the dots. The statement negative, let's go negative 7 equals 7, right? That is a false statement. But if I square both sides of this false statement, well, negative 7 squared is 49, and 7 squared is also 49. And what's fascinating here is that if you start with a false statement, a certain kind, and you square both sides, you may end up with a true statement. And that situation is what produces extraneous solutions. But more on that in a little bit. Let's just solve a normal one first. So this radical equation can be solved like any normal equation by applying the inverse operations in reverse order. So the first thing I would do here is subtract 10 from both sides. And that would give us the square root of 5x minus 9 equals 6. Okay, I'm going to pause for a minute right now, and I want to bring a graph into this, a visual aid into this. Here on the left side of the equation, we have a square root function. On the right side of the equation, we have a constant. And so here's what the graph of each of those looks like. Here the light blue is our square root function, and the purple is our constant function. And if we go over here right there, we can see they intersect. Right here they intersect. Where do they intersect? They intersect at 9. That's going to be the solution to this equation. Don't mean to spoil it, but let's keep going. So we're applying the inverse operation. Well, the next thing we have to deal with is this square root. And the inverse of a square root is a square. So we would square both sides. That would cancel out the square root, bringing down 5x minus 9 equals 6 squared is 36. Okay, I'm going to pause again. You're like, goodness, he's taking forever to solve this. Trust me, it's worth it. Check this out. On the left side of the equation, we now have a linear expression. On the right side, we still have a constant. But if we graph both of these, right here, here's my 5x minus 9, and here's my 36. 36 is up here. Okay. These are the two graphs now that we've squared both sides, and we see that they intersect also at 9, right? So the original two intersect at 9, these intersect at 9. But another point I want to make is that the two new graphs still only intersect once, right? That'll make sense later. Anyways, let's finish solving this. The moment you're like, dude, just get on with it. We add 9 to both sides. Those cancel. And we have 5x equals 45. Divide both sides by 5. Canceling those out. And 45 divided by 5. Well, there it is. There's your 9. And the answer here is 9. So that's it. Nothing crazy about this problem. It's just like solving any 1-step, 2-step, 3-step equations. This had 4 steps, right? Okay. Good. All right, nothing funny there. Now let's make things a little more interesting. Here we go. We have another one. I'm gonna get my graphs ready. Okay, so right away we have a square root. Right, we have a square root. That's the first thing we're gonna have to deal with. We need to get rid of the square root. The inverse of the square root is to square both sides. So we're gonna square both sides here, and this gives us 9 minus x equals x plus 3 squared. Now, x plus 3 squared, what is that? What is x plus 3 squared? Well, let's work that out off to the side real quick. X plus 3 squared. Well, that's x plus 3 times x plus 3, and you need to FOIL that. That would be x squared plus 3x. Plus 3x plus 9. Combine like terms in the middle there. 3x plus 3x is 6x. So all of that by itself is just x plus 3 squared. Good. Let's incorporate that into this problem. I'm going to zoom in over here now. So that means we have 9 minus x equals x squared plus 6x plus 9. All right, pause real quick. So I want to go back to the original problem here, and I'm actually going to delete these squares just so we can see it a little bit better. On the left side of the original equation, you have your square root term, your square root function. And so the graph of that looks like this. Right, there's the graph of that right there. And then on the right side of the equation, you have a linear expression, and that looks like this right here. And we're trying to figure out when these equal each other, which is going to be where they intersect. And there it is right there. They intersect at 0. So surprise, the answer to this problem is going to be 0. But I also want to look at this right here. After we squared both sides, I'll go ahead and bring that back now. After we squared both sides, we ended up with a linear term on the left and a quadratic term, or term, not term, but quadratic expression, function on the right. And that is what these look like. So let's see, I want to hide those. Bring these back. Okay, and notice here that this time the graphs intersect at 2 places. Now they still intersect at 0, which is where the original 2 intersected, but we're also intersecting at -7 now, which is kind of interesting. So what is this -7 about? Well, we'll see. We'll keep going here. All right, let's continue solving. In one step, I want to subtract 9 from both sides, and I'm also going to add x to both sides. I'm also just going to flip everything around and put the x squared first. X squared. Right here, we have 6x plus x. That is 7x equals, the 9's cancel out on both sides for a 0. All right, we got to solve this. How do we solve this? We solve this by factoring. Factor out an x. That leaves behind x plus 7. And then split up and solve each of these. So for the first piece, x is going to be 0, right? That's the intersection of 0. We can see right here. And then here we also have x plus 7 equals 0. Subtract 7 from both sides and you get -7. Okay, there we go. So that's where the -7 came from. It came into play. But just again, I'm going to give you the context here, is if you're looking at the original 2 graphs, they only intersect once. But after you square it, you get 2 graphs that intersect twice. So it seems to be introducing this additional possibility, this additional solution. That's a lot to look at. So let's check. Watch this. We already know that 0 is a solution. Well, it's worth doing. It's worth doing here. Let's check. I want you to see this. We have these 2 solutions, which contradicts the original graphs. Let's plug in x equals 0 into this equation, and we would have 9 minus 0 square root equals 0 plus 3. And 9 minus 0 is 9, 0 plus 3 is 3, the square root of 9 is 3, and 3 equals 3. So there we go. Okay, the 0 checks out, right? That worked. We like that. But what if we check x equals -7? We would have 9 minus -7 under the square root equals -7 plus 3. All right, 9 minus -7, that's 9 plus 7, which is 16. -7 plus 3 is -4. Square root of 16 is 4 equals -4. And that is false. That is false. That is not true, right? So that right there is why that is showing that -7 is an extraneous solution. And again, it seems so close. It's like, wow, you get 4 equals -4. Like that almost worked. Well, this goes back to what I started the whole video with, is that you can take this statement, which is not true, and you can square both sides and make it a true statement, right? If we squared both sides, we would get a true statement. And that's what happens. When you square both sides, you take something that would have otherwise been false, making it true, introducing another possible solution, but that still doesn't work for the original. And that right there, that's an extraneous solution. So, good, there's all of that right there. All right, it only gets more fun from here. So, we got 2 more examples. Let me get the graphs ready. All right, here's the next one I want to do. So right here we have our square root function on the left, and then we have a quadratic function on the right. So let's see what those look like. That's what we're dealing with right now. And they intersect twice at 1.732 and negative 1.732. You may or may not recognize that number yet. You'll see it soon here. Those intersect twice, which means that it will have two non-extraneous solutions. It will have two valid solutions. But of course, we are going to square both sides to get rid of that square root. So square this, square that, and we would have x squared plus 1 equals. Okay, you need to FOIL this, and I'm not going to do that again. That would be x to the fourth minus 2x squared plus 1. So after you square both sides, this is the equation you're dealing with. And on the left now, we have a quadratic, and on the right, we have a quartic. So what do those look like? That's what this looks like now, and we'll see here that it's intersecting in the same two places as before, the 1.732 and the negative 1.732, but we have this new intersection at 0. Well, you already see it coming, right? That is going to be the extraneous solution, but let's take the journey here and solve this. We would subtract x squared from both sides, and I would also subtract 1 from both sides. Good, and that's going to leave us, if I rewrite everything on the left, x to the fourth minus 3x squared equals 0. All right, we're going to solve this by factoring, pull out an x squared, leaving behind x squared minus 3. All right, split them up. X squared equals 0. X squared minus 3 equals 0. Okay, for the left one here, I would just square root both sides, and you get x equals 0. And then here, I would add 3 to both sides, and then square root, so x equals plus or minus square root 3. So, I apologize if I'm losing you in the details, but I'm assuming that you know how to solve by factoring. I'm assuming you know the square root property. So, we have 3 solutions here, and, well, there it is. This 1.732, that is the square root of 3, right? We have the positive and the negative, and then we also have the 0 right here. And 0 is going to be the extraneous solution, so let's check. Let's just check positive root 3. We don't need to check the positive and the negative. There's the symmetry there. But let's check positive root 3. Check x equals positive root 3 here. So what's the original? The original equation is square root of x squared plus 1. So root 3 squared plus 1 square root. Is that right? Yeah. And then equals. And then the other side was x squared minus 1. So root 3 squared minus 1. All right, let's check this out. So right here, this root 3 squared, that'll cancel, just leaving you with a 3 plus 1 underneath the root. Same thing here, those will cancel. 3 plus 1 is 4. 3 minus 1 is 2. And the square root of 4 is 2. 2 equals 2. There you go. Okay, so that works, right? It'll be the same thing with negative root 3. Since you're squaring them, the negatives will go away. The square of a negative is a positive. All right, so that worked. But then we have this suspicious x equals 0. Let's check that. Check x equals 0. And that would be 0 squared plus 1 square root equals 0 squared minus 1. All right, 0 squared plus 1 is 1. 0 squared minus 1 is negative 1. And the square root of 1 is positive 1. So here you go. 1 equals negative 1. Well, that is false. That is not true, right? So close, right? So close, so close. It's almost wanted it to happen. And again, I'm just going to keep repeating. I'm going to keep showing you that the reason why this happens is because at some point in the problem, you take what is a false statement such as 1 equals -1, you square both sides, and that makes it a true statement. Because of that, you are introducing an extraneous solution or extraneous solutions into this problem. So there they are. The solutions are plus or minus √3, which is about 1.732, and then we have this extraneous solution at 0. And of course, we see the intersections. If you look at the original, you see the intersections at plus or minus √3, but you don't have the intersection at 0 until you square both sides. There's the whole thing right there. All right, we got one more. Here is the last one. All right, so let's look at this graph. Let's look at the graphs first. We have root x squared plus 14. That's what that looks like. And then we have x squared plus 2. So that's what that looks like. All right, so we have two intersections right here. We have two intersections at plus or minus 1.414. We'll see what root that is in a minute if you don't recognize it. And all right, let's look at the graphs. Well, okay, so I would square both sides, right? The first step here is to square both sides to get rid of the root. And I would have x squared plus 14 equals, if you FOIL this, you would have x to the 4th plus 4x squared plus 4. Okay, cool. And let's look at the graphs of those. So remember, the original two right here intersect twice. These intersect twice. If there are extraneous solutions based off of this video, you would expect these to cross more than twice. But if we look at the new graphs after we square, I got to zoom out here a little bit. Okay, here we go. They appear to only be intersecting twice at the same places, plus or minus 1.414. So, okay, based off these graphs, there must not be any extraneous solutions. But let's go ahead and solve and see what happens. I would subtract x squared from both sides. And 14. And then I'm going to put everything on the left. All right, everything on the left. Here we have x to the 4th plus 3x squared minus 10 equals 0. Okay, if you factor that, you will have x squared plus 5, x squared minus 2 equals 0. Solve these. X squared plus 5 equals 0. X squared minus 2 equals 0. Okay, on the left, I would subtract 5 from both sides, and then I would square root, which would give me plus or minus I root 5. Yes, the square root of a negative gives you I, so I has just entered the chat. Now we would add 2 to both sides on this other side, take the square root, and we'd have plus or minus root 2. So there you go, plus or minus root 2. Root 2, that's your 1.414 that we've been seeing on the graph. So there's that. And well, here's the reason why we haven't seen any other intersections. That's because there are 2 more, but they're complex, right? We kind of need 4 dimensions for that, and that's not going to fit on this graph. So don't be fooled. The first 2 graphs intersected twice at plus or minus root 2. After we squared both sides, we got 2 other graphs that intersected at the same place, but that didn't mean that there weren't extraneous solutions. So let's go ahead and test out. Let's just test out the positive ones. Let's test out the positive root 2, and then we'll test out the positive I root 5 and just see what happens. So check, check positive root 2. Let's start there. Check root 2. And again, we want to plug this into the original equation, which was x squared plus 14 underneath a square root equals x squared plus 2. All right, good. So the square root of 2 squared, well, the root and the square will cancel, so that's just 2. So we have 2 plus 14 underneath the root here. And then over here we have 2 plus 2. All right, so 2 plus 14, that is 16. And 2 plus 2 is 4. The square root of 16 is 4. And there you go. You get a true statement of 4 equals 4, implying that root 2, I should have put x equals root 2, is a solution. Now, let's check... What do we say? We're going to check the I root 5. Check I x equals, that looks more like cheek than check. Check x equals I root 5. Now, it's okay. Don't be intimidated by the I. Be fascinated by it. This is going to be pretty cool here. I want a straight line, though. I want a straight line. There we go. Okay. So I root 5. We're going to plug I root 5 into this. So that would be I root 5 squared plus 14 all under a square root equals I root 5 squared plus 2. All right, so we got to simplify this. I squared is -1. Root 5 squared is 5, so that's going to be a -5. -1 times 5. Same thing over here. This will produce a -5 plus 2. All right, -5 plus 14. What is that? That is 9? Yeah, nice. And then -5 plus 2 is -3. The square root of 9 is 3. And there it is again, right? So there it is. You get a negative number equals a positive number of the same digit, of course. But that's not true. That's not true. 3 does not equal -3. And I'm going to say it one more time. This is where the extraneous solution comes through, is you have what would be a false statement. This is a false statement, but I can take this false statement and I can square both sides. If I square both of these, I would get 9 equals 9, which is a true statement. And that's what's crazy about these, is you have something that would otherwise be false, but because the problem requires you to square both sides, you end up introducing extraneous solutions. You may introduce extraneous solutions. Sometimes you will see those on a graph, but this last example we did not, because the two extraneous solutions were complex. But anyways, I hope you learned something from this. Thank you for sticking around. We'll see you in the next one.